Welcome to our webinar, DecarbonICE, Maritime Transport of CO2 in Frozen Pelletized Form Carried in Box Containers. Our guest speaker today is Henrik Madsen, CEO and co-founder of our sponsor, DecarbonICE. He'll be answering any questions you may have after a presentation taking place shortly, so please leave them in the Q&A section of your screen. Now over to our CEO, Carl Jeffrey, to start the talk.
So we're going to talk today about moving carbon dioxide as frozen pellets in box containers. So why do we need that? Well, we're getting more and more carbon dioxide capture sites around the world, more and more storage and utilization sites, and more times we're looking for ways to move the CO2 from a capture site to a storage or a utilization site, and where we don't have a pipeline. Building new CO2 pipelines is expensive and often gets public opposition. And moving it in liquid form by sea in tankers means you probably need to sign a 15-year agreement to charter one. And that only works if your capture site is next to a tanker terminal. So another option is to carry CO2 in box containers using the existing box container transport network by road, rail and ship. We can freeze the CO2 into dry ice pellets. And if we put 25 centimeter thick insulation around the box, that's enough to keep it at minus 80 degrees C, so it stays frozen in atmospheric pressure without a refrigeration unit. And the container can be used for intermediate storage as well as transport. So our company presenting today, DecarbonICE, did a pilot project moving a box of frozen CO2 pellets from Århus in Denmark to Reykjavik in Iceland. They saw a boil off of just 0.3% a day. And our speaker today, Dr. Henrik O. Madsen, is going to explain. Henrik is founder of DecarbonICE, and he's also a former president and former CEO of DNV. DecarbonICE is supported by the Danish Board of Business Development, the Danish Maritime Fund, Maersk, Imskip, and Total Energies, among others. And we'll have a talk from Dr. Madsen of about 25 minutes, and we'll take your questions. So, Henrik, I'd like to invite you to start your talk.
Thank you very much, Carl. And thank you to all of you for listening in. So what I will present is an innovative solution for maritime transport of CO2. The solution is radically different from the incumbent solution of transport in liquefied form in CO2 tankers. We believe that over time we will see several solutions used for transporting CO2 at sea. But it's a very young industry, so we think there's plenty of room now for innovation. We believe the industry will become very large. If we look at various scenarios, they all talk about an industry for carbon capture, utilization and storage, or CCUS, by 2050 of the same size as today's coal industry. And a lot of the transport will be at sea, because of the distance between the CO2 emitters and the utilization sites. At the center of the presentation is our container, the decarbonized container. Here you see it on a truck in Iceland. So it says DecarbonICE, the coolest way to cut CO2. But before we go into details on the container, we have to do a small physics lecture. Because it's important to understand a little bit about the physics of a CO2 to understand how we move from one phase to another. And this picture shows on the x-axis the temperature and on the y-axis pressure. And CO2 can exist in 4 forms depending on temperature and pressure. You have the yellow part, which is a gas form. And of course, in the atmosphere, CO2 is in gas form. You have a greenish part, which is a liquid form. Then you have to the upper right, rosa form, supercritical fluid. So a supercritical fluid is really a fluid, but behaves like a gas. So it's quite funny. So if you have a pipe, the whole pipe would be filled, but then you can move it like a fluid. And then you have to the left, the solid CO2, which we call dry ice, and which you may know from school or from parties or from theaters and so on. And this is this is the form we want to transport it in. When we transport stuff, it's important that we have a high density to reduce the volume. So the density of liquid CO2 is around 1 ton per cubic meter, like water. The same for supercritical fluid. In gas form, even at 50 bar, the density is only 1/10, so 0.1 ton per cubic meter. And solid CO2 has a density of 1.6 ton per cubic meter. I will explain later, we transport it in pellet form, so that it will not be completely filled. There will be some empty spaces between the pellets. So the effective density is also around 1 ton per cubic meter. Another thing we can observe is that liquid CO2 cannot exist at a pressure less than 5.1 bar at this so-called triple point. And normally in liquefied CO2 transport, we will be at 20 bar. So then the temperature, or then if the pressure goes below that 20 bar, then it cannot be in liquid form. Another thing we observe is that if we go to the very left corner and have solid CO2 and then add heat so that it will move, temperature will increase, it will move to the right, it will go directly from solid CO2 to gas form CO2 without a liquid phase. We call this process sublimation, so you'll hear me use that word, maybe, but think of it as something evaporating, but there's no liquid phase in between. So that was a little bit on the physics. Then a few words on incumbent transport solutions. Carl mentioned a little bit. So pipeline in supercritical form on land may be the most efficient, but you need to have large volumes, and you need to have the people living along the route to agree to it. We don't have such trunk pipelines in Europe yet, but there's a network in the US that has existed for quite some time and is being further developed. Carl also mentioned by truck in liquid form, and the tanks there are pressurized cryogenic tanks, normally say 18 to 20 bar pressure, and the associated temperatures are minus 20 degrees Celsius. By ship, it would also be the incumbent solution is in liquid form in pressurized cryogenic tanks of type C. And this transport has actually existed since 1988, where the first ships were launched by Reykjavik Shipping. And there are very few ships operating like this now, but they have all operated safely and they have very competent crews, so there have been no accidents. And the latest ships of this type are for the Northern Light storage in west of Norway. And these ships are just being delivered and put into operation now. But we talk about less than 10 ships in operation. There are some developments on the ship transport. The Northern Lights vessels and the Reykjavik shipping vessels have about 20 bar pressure. There are now work going on to get the pressure down to maybe 8-9 bars, because then you can have a lighter type C tank. These concepts have been pre-approved by class societies. And there's also a concept going to the other end by trying to transport in supercritical form, then at ambient temperature. And the ship owner Knudsen NYK Carbon Carriers has suggested that based on their compressed natural gas technologies. But our idea to transport CO2 in solid form in bulk has not been neither proposed nor implemented. At sea, a little bit of dry ice is transported at sea, but in small boxes and mainly used for cooling the food on board a ship. I said that CO2 can only exist in liquid form under a fairly high pressure. And it means that there is a risk of an accident if the tank is depressurized. It could be that something penetrates the tank or that the main valve fails. This is a very famous tank accident with a tank truck from Mainz in 2015. It was on the 23rd of December. in the center of Mainz, and you can imagine the day before Christmas, the center was full of people at the Christmas markets. So the valve failed. The CO2 inside the tank was depressurized, and then the white cloud you can see is then dry ice and condensed vapor, water vapor. There's also a very high concentration of CO2 at a very low temperature. So both the dry ice and the very cold CO2 gas is heavier than atmospheric air, so it sinks to the ground. It removes the oxygen, so actually people can die from being there. Fortunately, nobody died because the fire brigade was very quick in moving people away. But if you go on the web, you can find some spectacular accidents, both with pipelines and with tank trucks. Then let's look at the DecarbonICE innovation and just start with looking at it at a glance. So in our concept, we'll transport CO2 in solid form under atmospheric pressure. So we are at the very left corner of our phase diagram. So 1 bar pressure and minus 78.5 degrees centigrade. I can say in terms of philosophy, this is a little bit similar to transport of LNG on a ship. It also happens at a very low temperature, but at 1 bar pressure. So in terms of safety, at least I kind of like on ships rather to have a low pressure and then maybe associated with a low temperature than to have a high pressure. The dry ice pellets we produce from dry ice machines. I'll talk about them. And I'll talk about our standard 20-foot reefer container with additional insulation. And by moving to containers, we can use an existing transport network, which is one of the very big advantages of our concept. So the container can be moved by trucks, by ships, by trains, by barges, and without any intermediate reloading or reconditioning. The container can act as an intermediate storage, and it acts as a tank for transport. And then once the dry ice container has reached its final destination, we can then convert the dry ice back to gas or liquid phase, because at the final location, we probably want to either store or utilize the CO2. So let's go into details on the different elements. And we start with the dry ice machine. We basically have two large producers at least in the Western world. One is called the Cold Jet, the other is called ASCO. And they have very similar products. Here I have some data for the Cold Jet, the largest Cold Jet machine that you can buy now. And this one, I think you can buy it on Amazon. So it's a really well-known technology. So you see the production capacity is 750 kilo per hour of pellets. You see the dimensions, the weight, so it doesn't take up a lot of space. And what happens, and I'll come back to that a little later, is that we don't get 100% dry ice pellets when we use the machine. The cost of this could be maybe 200,000 euro, something like that, so it's not terribly expensive. ColdJet, that is our partner, is now making a solution where in a 20-foot container frame, we can put two machines that are double this size. So then they will produce 1.5 kilo per 1,500 kilo per hour, and they can we have room for two of these in the frame. So from one 20-foot container frame, we could produce 3 tons per hour, 72 tons per day, and something like 25,000 tons per year. So you see just one machine can actually produce a lot of dry ice. But how does it work? Well, to produce the dry ice, we start with liquid CO2. So there has been a capture plant on the emitter side, and that plant delivers CO2 in liquid form. We're quite agnostic to how it happens. We just want it in liquid form at a pressure of some 15-20 bar. Then we have the liquid CO2 in a fairly small tank, and we run it through the dry ice machine, the pelletizer. the pelletizer doesn't really use any energy itself, but what happens when we depressurize the liquid CO2 is that a so-called adiabatic process happens, and there's no heat exchange with the surroundings, but in that process, 45% of the CO2 becomes dry ice and 55% very cold CO2 gas at maybe minus 70 degrees. Then we need to take that cold CO2 gas and liquefy it again, because we really want the machine to be able to produce almost 100% dry ice. So that here you see a CO2 recovery unit that will then liquefy the 70 or the 55% cold CO2 gas. Ideally, we want to use the machine, the liquefy machine from the capture plant, and that's what we are aiming to do. But we get an operational cost here because we need some electricity for the recovery of the CO2 gas, and the cost, well, depending on the cost of electricity, is somewhere between 10 to 20 euro per ton. So that's an OPEX we have to carry, and which the incumbent solution of transporting in liquid form does not have. But we believe that extra OPEX is more than paid for by the savings on the transport part. Then let's move to the container, sort of the core of the innovation. So we take as a starting point a standard reefer container, but we increase the insulation from, maybe 6 to 8 centimeter to 25 centimeter insulation. And the insulation is a so-called poor insulation or polyurethane insulation. That insulation leaves enough space inside the container to carry some 20 to 22 tons of dry ice pellets. And this is exactly the carrying capacity of such a 20-foot container. So we have kind of found a sweet spot here. We don't have any active cooling of the container, only the poor insulation. So some heat will come from the outside into the container. But because of the good insulation, the loss of CO2 because of that is only 0.3% today, which we find very acceptable. Then the small part of dry ice that sublimates will then build up a little pressure inside the container, which we don't want. So we put in safety valves that are set at 1 bar so that any CO2 gas that is formed is then sent to the atmosphere. Oh, sorry. We have a partner to do the container. It's Maersk Container Industries, one of the very largest producers of reefer containers. And the demonstration container I showed you before, and I'll show you again, has been donated by Maersk Container Industries. And they're helping us to make the final design. And just to repeat myself a little bit, by using standard containers like this, we can use the existing worldwide container transport network system. We don't have to construct a lot of new containers. We just use the existing system. We don't need to build any particular infrastructure. It already exists. And you saw the container in Iceland. It came there by ship. We have also, by Deutsche Bahn Cargo, Scandinavia has taken the container on one of their cargo trains. So it works, and there are no intermediate storage. And we believe that the advantages of this are really very, very big. The container is safe, so we don't have any large safety zones for intermediate storage. Then we move on to the reliquefaction units. Because at the final location, we want to bring the dry ice into either gas form or liquid form. The gas form may be for a PTX plant. The liquid form may be to storage equipment that will store the the CO2 in deep geological reservoirs. Our suggestion for reliquefaction unit is very simple. You see a pipe that can act as a pressure vessel. The pipe is made from either aluminum or austenitic stainless steel because they can adopt, or they can handle the minus 80 degrees centigrade. We can open the pipe at the top and pour in the pellets from the container. And if we have a 1 meter diameter, 20 meter long pipe, we can handle one container. Then heat will come from the outside and the pipe is not insulated. So if we go back to the phase diagram, dry ice will start to sublimate, the pressure will build up, we will reach the so-called triple point, then it will start to melt. Once everything is melted, it will heat further, and at the end we will have a mixture of liquid CO2 and gas CO2. And we have made the scale experiments to show that this actually takes place. To get the energy from the outside, we preferably submerge the pipe in seawater where you have a flow from waves or current, but it can also work on land and it will take a little longer. Our calculation so far tells us that we can fully liquefy such a pipe in, say, 4 to 6 hours. And you can also understand that any port can install these such a plant. We could also be lucky that there maybe is a need for cooling energy where we at the final location for a data center or something else, and then of course we can sell the cold energy from our dry ice to maybe a data center or something else. Just a few words to how we get from the emitter to the port on land. Yeah, so it can be in our containers, it can be by train or by truck. And I'd just like to mention trucks or trains also, because each standard wagon can carry 3 containers, and the train can be 50 wagons long. So we would be able to transport 3,000 tons per round trip. So let's say a round trip take a couple of days, for instance, from central Germany to the port of Wilhelmshaven or up to Denmark. Then each train can really maybe do half a million tons per year. So trains can be a very good way to transport on land, but of course otherwise trucks and many small emitters will only rely on trucks, which can then bring the containers maybe to a train station or to a pipeline where it can enter a pipeline. At the port, we don't really need a lot of facilities. We come in with the containers, with the full containers, take them off, and then we put an empty container on, and it goes back to the emitter. So you need one area with filled containers and one area with empty containers. And then we need the area for reliquefaction of the full containers. There's really no risk related to this equipment in the port, because there's atmospheric pressure inside the containers. The sublimation is very low. There's always some movement of the area, so we don't build up CO2 concentration at a ground level that can be dangerous. But of course, we will need some monitoring in the port. Then let's go deeper into the ship transport and the technicalities around that. So let's assume that the ship is a standard container carrier, but of course there are other ship types that can also carry containers, and we can think of barges for shorter distances. The container carrier can have its own cargo gear, but it's rarely necessary because the port will have such a cargo gear. So what are the rules that apply for transport of dry ice? Of course, the existing IMO conventions, codes, and so on, other industry instruments, they were not developed for transport CO2 in bulk. And like for other forms of maritime transport of CO2, we have to do a proper risk analysis to show that we are in compliance with the principle behind the IMO. and IMO has very good guidelines for doing such a risk analysis. And together with DNV, we have performed a real thorough hazard analysis for our transport. What you see from this a little busy slide that dry ice has a Euro number 1845, carbon dioxide solid. They are also, because there's a little bit of dry ice transported on ships, mainly, as I said, to keep the food cool. And they are in styrene bags or boxes. It says they have to be on the deck only. And there are a few things that is in the rules, but again, the rules were not made for our solution. So we work with the DNV and with flag states to prepare them for being able to approve our solution. And we can say the current IMD Dangerous Good Code, for instance, it has no instructions for bulk containers. When we did the transport to Iceland, we had the container on deck, and that container was actually treated like any other container. We had received an exemption from the flag state, the Faroe Island flag state, and it was an Eimskip container ship called Borfoss, 2,150 CU container ship. So we did one round trip with our container on deck. Of course, the crew knew about the container, but they handled it just like any other container. And to the left, you see, at the lower part, you see the white container, just like any other container in the stack. And to the right, you see me touching the container just to verify that the outside temperature of the container is almost like the other containers. It was maybe 1 or 2 degrees colder. During that voyage, we could also confirm the sublimation, the loss of CO2, 2.3% per day, based on a full container situation. And that was measured over a 10 days trip at sea and in port in Iceland. So that was very useful to verify some of our assumptions. So in the work by DNV and this hazard work, we have identified one area which needs more attention, and it's what to do if we want to store the containers on the deck. On deck, there should be very few problems, but of course we have to have some monitoring to see that we don't have CO2 gathering in certain places where people may come. But below deck, the sublimation will bring CO2 into the cargo hold between the containers, and within a few hours, a cargo hold will be filled with CO2 gas. So we then basically have 2 options. We can either use the cargo hold ventilation system, and we've checked with some container feeders, and it has plenty of capacity to get the CO2 gas out. Then, of course, we then get quite humid atmospheric air into the tank. The other option is to allow the tank to become inerted and become completely full with the CO2 gas. And additional CO2 gas we then vent to the atmosphere from a safe location on the deck. And of course, operating inerted tanks is well known from oil tankers in ballast conditions, and crews know what to do and what's not to do when they enter some tanks. We are also doing calculations on what will the temperature be within such a cargo hold to make sure that we are not below 0, so that ice will not form, particularly on equipment that we use for lifting containers. So there's still a little bit of work to be done here. We're quite comfortable that it's fine, but we will also have to show it to the authorities. In terms of operation of the ship, the hazard did not show any showstoppers. Of course, we need some measurement devices to make sure that CO2 doesn't build up in critical points. We need to make sure that the cargo ventilation outlets are not close to inlets to the engine room or accommodation. But all of that should be quite straightforward. Then comes a very interesting comparison, because how does the capex compare for a liquefied CO2 tanker to one of our vessels? And if we look at option 2, it's the 20,000 cubic meter liquefied CO2 tanker. This is the size that's often suggested as the next size. And we have a new building price around 110 million euro. Northern Lights have put that number out, so it's not something I cook up. And that includes the C-type tanks on the ship. Then we need 2 intermediate storage tanks, one at each end. Northern Lights would propose 30,000 cubic meter. It may be one tank or a number of tanks, and that would cost around $13 million, so $140 million altogether. So with our option, we would use a 2,000 TEU container feeder vessel. That has enough deadweight capacity to carry 1,000 fully loaded dry ice containers at 21 tons each, so the same carrying capacity. Such a new building costs between 30 and 45 million US dollar. But I'd say if we don't need a new building here, like with the liquefied CO2 tanker, we can buy an existing container carrier, and a 10-year-old 2,000 TEU feeder cost maybe 10 million, or we can just charter a vessel. So we can get started very, very quickly. When we have 1,000 fully loaded containers on board the ship, there will be 1,000 containers being filled at the emitter site, and there will be 1,000 containers being emptied at the final storage site. So we need totally 3,000 containers. They cost between 6 and 8,000 euro per container, so that's another 15 million US dollar. But you see, there's no intermediate facility needed in the port. So total, we end up maybe at 45 million, maybe less, maybe a little more. So it's 60% lower than for the liquefied CO2 tanker option. So particularly when we have a maritime transport, this extra OPEX I talked about in the beginning to produce the dry ice, we believe is more than fully compensated by the lower cost for the transport. So let me come with a few conclusions then. First of all, there will be a tremendous need for CO2 transport in the future, and a significant part will be at sea. We have liquefied CO2 tankers. The concept has been in operation since 1988. It is proven, it is safe, it works, but it is quite expensive. And we don't have many ships today, so the shipyards really have to build them, and you probably need to have, as Carl said, a contract for 15 years. So the willingness to take such a risk is not very large. There's in general a significant need for upscaling, as I said, but there's also room for innovation. And we saw from the small physics exercise that CO2 can exist in, and it can be transported in 4 different phases. Our decarbonized solution is radically different from incumbent solutions. And I can also speak from experience, it takes an extraordinary effort to challenge incumbent solutions, which is why we're very happy to have this webinar. And also just to review a few of the advantages, we transport at 1 bar pressure. So our solution is very safe. I would almost say intrinsically safe. And even if something happens with the container, the sublimation is very slow, so you don't have a lot of CO2 coming out very fast. Our solution is easy to scale. We can, as I said, charter existing container vessels. Containers can be made available with very short notice. We can buy new containers, or we can remodel existing containers. Our solution does not require any particular training of neither ship crew or port staff, because it's very safe. we can mix containers with other cargoes, which means that we can easily do a gradual build-up of capacity. The port facilities for handling dry ice containers are safe and simple. Container ships and containers can be reused once we are finished. And then I have a last point, which maybe we can discuss a little bit. We see few, if any, corrosion issues with our solution. And corrosion is quite a critical issue for pipeline and liquefied CO2 tanker transport. And then we saw that our solution is a lot less expensive than incumbent solutions in all our example cases that involve maritime transport. So with that, thank you very much for listening, for your attention. And I send it back to you, Carl.
Well, thank you very much, Henrik. So that's great. So we've got 3 questions already. We're open to questions if you'd like to put them in the Q&A box. So we can go. So Lucy Shorbay, I've been looking you up on LinkedIn. So you're team manager, industry decarbonisation, carbon management at Air Liquide Innovation Campus in Frankfurt. So first question is about the maximum duration of the transport. What is the risk if a dry ice container is forgotten or stuck somewhere for many weeks? So I guess we talked about 0.3% a day. Does that mean 300 days you don't have any CO2 left? But it would ideally a lot shorter than that.
No, so if we kind of lose 60 kilo a day, it's very little. I mean, you know, a car, if a car burns 20 liters of gasoline, it's 60 kilo, just to give a comparison. So I think there's enough wind in most locations that it will not be an issue.
Yeah, I suppose there's practical concerns. I mean, if you had 200 containers in a terminal,
sure,
they're going to be there for a week. I guess people might ask questions about the.
Yeah, and for sure you need to monitor what the CO2 concentration is on the ground. Yeah.
Oh, very good. And second question from Lucy about the electricity consumption for the pellets production from liquid CO2. I guess I would have thought most of the energy goes into making it, liquefying it, which happens upstream of isn't it? But do you want to talk about that?
Yeah, so you have a higher energy consumption upstream to make it liquid, for sure. But we have this additional cost of going from liquid to pellets. As I said, 140 kilowatt hour per ton is what the dry ice producers say. Maybe it's a little higher. So in our calculations, sometimes we use maybe up to 200 kilowatt hours per ton.
Wow.
And if you use an electricity price, say 8 € per ton, then you get maybe 15 euro per ton.
Wow, very good. So Klaus Genstrup, I think LinkedIn says he's technical service manager at DNV in Copenhagen. So you probably know him, or maybe he's saying, with respect to the example, the price example, I think not price, I guess the pelletizer machine should be included. But then if you've got a tanker carriage, you're also including the pipeline. So I guess more a comment really, isn't it? But
no, sure. We have to look at the whole value chain, but I just wanted to show CapEx numbers for the ship itself.
Wow, very good. So Razik Raja Ibrahim, I haven't looked you up on LinkedIn yet, but it says there's a comment, there's no corrosion. What about if the CO2 has impurities like hydrogen sulfide? I think he could be an engineer with Mitsubishi in Japan. There's somebody with that name.
Yeah, well, you can say, when I say there's no corrosion,
that's right.
Because, there's no free water because the pellets are minus 80 degrees. We are discussing with the dry ice machine producers how clean CO2 they need to operate the dry ice machines. But ideally, from the dry ice machine, you receive very clean CO2. But yeah, let's put it like that. It's a good question. It's a question that we investigate. And also, when we return a container, we also need to make sure that we don't have any condensation and can get carbonic acid that can cause some corrosion. And the same in a cargo hold. If we bring in a lot of atmospheric air from the outside with a high humidity, together with CO2, that the carbonic acid will form, but it takes a long time to prepare or to corrode. But we have to check the cargo hold sides and the tank top to make sure that we don't have corrosion. But you can check that during the normal inspections.
Yeah, it could be a lot simpler than when we hear about these big pipeline networks. They have a lot of discussions about exactly what specification they're going to accept, and everybody has to agree on it. But with this one, you might have the transport company owns the container themselves, so they just got to agree it with the storage, and then the specification for storage maybe doesn't matter so much, I suppose. He also...
the storage providers also have very strict requirements on CO2. I think personally they're too strict. But of course they don't want the casing in the well to corrode, but still, where the well ends, there's a lot of stuff that they can't control anyway.
Yeah. And then he's also asking, any specification. I guess we've answered that. Any specification for the CO2? I guess you're not setting any specification, but it's just want to think about making sure that the freezing works fine. That's the important part, isn't it? And,
and you can say that the dry ice machines are made of material that doesn't corrode. So,
Very good. So Arvind Sharma, I know you've asked us questions before, Arvind. I forgot which company you're from, but he's asking any connection with carbon capture and utilization systems on board. I think that means on board carbon capture systems. I guess you could.
So that's interesting, because the other day I had a call from somebody who produces a carbon capture on board using an amine system, and their idea was then to liquefy it and have it in sea tanks on board, and then pump it overboard to when they reach the port. And then we did sort of calculations in our head for, I think it was 25,000 tons a year, so not a very large vessel, that we could just have one of our dry ice machines and just a few containers, and then we could use our solution instead. And it would be more compact because we have like cubic containers, they have circular tanks, and safety. We wouldn't need a safety zone around the dry ice container, and it would be very easy to lift them on and off the vessel. So when you come to the port, you lift the container off, you bring an empty one on board. So I think also, but this has merit, but we just went into more detail a couple of days ago. So I'll be happy to discuss with others how we can do it. Because we now, there are a number of operators that now are able to capture the CO2 on board. So, but then how to get rid of it?
Yeah, so I've seen Arvind is manager technical efficiency with Mediterranean Shipping Company in Geneva. So this is probably looking at shipboard carbon capture systems as a, but I suppose the hard part with shipboard carbon capture is the carbon capture, not the handling of the CO2, I suppose, isn't it? Yeah. He says, "Thanks, Henrik. I'm going to contact you to follow up with that." So that's that sounds great. Well, one question going through my mind. So when we talk about these carbon capture networks, there's often a chicken and egg problem that companies can't start without having a whole chain in place to capture the pipeline and the transport. I'm just imagining, say there's a small emitting company such as Energy from Waste plant in central England, watching this thinking, well, can I do this myself? And where would I start? So maybe, I don't know if you want to think through, there's nobody yet agreeing to receive these containers, but presumably, well, you've got one client in Iceland. I guess that's a client works. I don't know if is that something, starting point?
Yeah, I'll say actually in our company, we'll start small. So we'll start by looking at biogas plants, waste to energy plants, as you say. And then there will need to be storage sites, and then they can store there. So most storage sites now are offshore, but Denmark is now very keen to develop some onshore storage sites. There are four companies have been given the right to develop onshore storage sites by 2030, and the capacity is enormous onshore, and of course the cost is much lower. So and Denmark is small, so it's maybe 200 kilometers maximum distance. Same in the UK, you can go from a biogas plant, waste to energy plant, and go to one of these hubs that you're developing on the East Coast. From the West Coast, you could also sail to some of these hubs. And you could also have kind of a milk route operation where you pick up a few containers here and there and go to the pickups and then do the storage there. So I think we supplement what is being developed by these hub concepts very well. And also those who build pipelines, they would have locations along the pipe, maybe where they increase the pressure, where they will be able to enter more CO2. So we don't see ourselves competing with pipelines at all, but we are more supplement to make the small emitters able to use the pipelines.
Oh, so it could be as simple as buying a pelletizer machine and buying one box to start off with.
Yeah.
I think that's
Yeah.
5,000 euros for one box. I think I worked out.
Yes.
But then we'd have to persuade one of these early CO2 storage projects to accept it, but that shouldn't be too hard. I wouldn't have thought of.
Sure.
Yeah, but
sometimes it's good to start small instead of going. Of course, it looks good. You can store 2 million tons a year, but I mean, maybe start small and then building it also from the bottom to the top here.
Yeah. Well, what about the apparatus for receiving it? I mean, you showed how it worked technically, but I guess you'd have to have some machine to put the box container on the top of this sublimation unit. I think that was the word. And
yeah, so that equipment we will also develop with. But I mean, we have many oil and gas people working with them. They're used to stuff like that. And when you export the liquid CO2 from the pipe to say a unit that will store it, it's just like that unit had received it from a tank truck. So this is just the same that they would normally do. And we can kind of deliver it at a temperature all up to the ambient temperature, because the longer we wait, the warmer it gets. And because if you had, say, come in at 20 bar minus 20 with a tank truck, maybe you need to heat it a bit, but we can maybe wait until we are at -5 or 0 degrees. So that could make it even easier for the storage plant.
You didn't say what you did with the container in Reykjavik. I'm guessing it was for the Climeworks project. Did they put it in the ground, or was it vented? Or
yeah, well, we took the container to Iceland. Yeah, so yeah, it's Capfix and Climeworks who do. So Capfix store for Climeworks. Yeah. With the Capfix, we have the idea that we could store in solid form, because the Capfix, their wells are about 1,000 meters deep, and they pump CO2 down in gas form. But since our dry ice has a very high density of 1.6 ton per cubic meter, we thought we could just make the pellets maybe into a ball and just drop it in the well. It would sink very fast. In a few minutes, it would be at the bottom. It would then melt, and it could start to react chemically to the basalt, and where you have the permanent storage. Yeah. So that's a kind of a very elegant solution. We didn't do that because the rules are so we were not allowed to bring dry ice from Denmark and take it out in Iceland. So we had to bring it back. The two countries have to make an agreement on that.
Yeah, I suppose most carbon storage the projects and the systems are handling solid CO2, but I suppose it's technically possible to do, but it's not something we have at the moment. So we're probably talking about.
No, I think technically we are far ahead than business model wise. I think the problem is the business model, is not the technology, to put it briefly, bluntly.
Yeah, so what would you ideally like to see next? You want more companies willing to try this?
Yeah, so I mean, we are just a technology company. We really like to share our ideas. We like to be challenged. We like to see maybe initially some biogas plants, waste to energy plants building a unit. And we'd also like to see train operators start to maybe move some of the containers by train. Trucking companies saying that, well, this might be an interesting business for us. And just start small. And some of the storage sites, like the Green Sand offshore Denmark, is ready to receive our containers. Yeah.
Wow, very good. So, question coming up from Gorgios Viliotis. What happens if a container got damaged while loading or discharging? So I think the point you were getting across in the webinar was it's a lot less problematic than if it was under pressure and suddenly froze and
Yeah, exactly. Yeah, so of course, if the dry ice is exposed to the atmosphere, it starts to sublimate, but this is a very, very slow process. And probably in those who have seen dry ice in physics, I mean, maybe the teacher just threw it on the table, and 2 hours later it was still on the table. Maybe some sublimation had been there, but it's very slow.
Yeah, I mean, I suppose it's also regulators would have a lot of concerns, but I suppose, yeah, well, yeah, you can show them, I suppose, isn't it? So you've got frozen
Yeah.
carbon dioxide that, I guess, would it make a, I mean, if it was heavy, I suppose it could melt slowly and you'd have a high concentration of CO2 around the box, wouldn't you? But I suppose it's also
You can just let it melt and make sure people don't get close to it, yeah, and maybe get rid of the container.
Yeah.
So in our hazard with DNV, these scenarios we looked a lot at, and our conclusion was that yes, a container may be lost during loading, unloading, but the consequences will be very low and fairly easy to handle.
Oh, very good. Yeah, I was just saying he's a fleet operator with ocean routes management in Greece. Yeah, so it's a lot of interesting questions. When you loaded it on Deutsche Bahn train, was there any regulatory challenges there? Is that something?
No, so Deutsche Bahn has just expressed a big interest, and they have the cargo part of Deutsche Bahn transports a lot, and also they transport a lot of waste to Denmark, for instance, for our waste to energy plants. So they're just very keen to take a role, and all big German factories which emit CO2, they all have rails coming into the factory. So it would be very easy for them to connect big German emitters with storage sites by rail. And Germany, of course, emits a lot of CO2 every year. And now the German legislation has been updated. So I think Germany, some say maybe it has been a laggard, but now Germany really looks forward to become a leader. But other rail companies and private rail companies can see a role for themselves.
Well, very good. So we've got a question in from Marcelo Firmapin. So there's somebody with the same name who's a global business developer, Air Liquide in Buenos Aires. I don't know if that's
Yes.
you. I arrived a bit later. Can you share about the loss of the CO2 during the storage and transport? So that was just something I put in my introduction, this 0.3% a day, but perhaps do you want to say a little bit more about the...
Yeah, so when we think we have a nice sweet spot with pellets and 25 centimeters of insulation, because then we can carry 21 tons, and the 20-foot container cannot carry anymore. I could also say we don't use 40-foot containers, but because the load carrying capacity doesn't scale up in the same way. That's why we go for 20-foot containers. If we ask the dry ice machine to deliver in cubes rather than pellets, then the density of the cubes would be 1.6. Then we would have room for 40 centimeters of insulation. And then we could get the sublimation rate down to 0.2% or 0.15%, something like that. But then the loading, unloading of the pellets of the dry ice would be a little more complicated. You'd have to open the door and do it more or less manually. With the pellets, we believe we can do it automatically, only relying on gravity. Yeah.
I mean, it's mainly the concern that the actual slow leaking. I guess that's what people will be concerned about.
Yeah, but we can get down to lower sublimation rates if we want to. Yeah. And of course, we use poor insulation. You may go to other insulations which are more effective, but then again more expensive. Poor is not very expensive.
Oh, very good. Well, I think that's very hard. I mean, it seems like a sort of solution that people aren't. We need to bring this into the overall mix of different solutions for moving carbon dioxide around the ground. I guess that's what we need to do now, isn't it? And I guess all the projects so far have been sort of very centralized, these point-to-point projects, but now it's getting far more, I don't know, fragmented is the word, or distributed CO2 systems. And I guess we want to see some kind of standard so you could have these containers moved around the world and people could know that perhaps you'd need this is the next kind of steps, but mainly want people to contact you and show interest and build a network of companies doing it, I suppose.
That's what we would like to see.
Yeah, well, that's very good. Well, it's coming up to the hour now. I don't know if there's any last words you'd like to leave our audience with, or you've got your email address there for people to contact you with, and
Yes.
yeah.
And like I said in the beginning, I think there's a lot of room for innovation in the CCUS value chain. So it's just for people to come up with ideas. And also one comment. So we say CCUS, and when I have a presentation, I often say, "Where's the T?" There's no T for transport. And it's also when you see money, they are allocated to capture or to storage. But now people really understand the T, the missing T is very important.
Yeah,
And I don't think there'll be one solution, there'll be a number of solutions. So we just need people to use their imagination. And then I always carry the CO2 phase diagram in my pocket because it's quite different from other gases or like water. So you have to think what happens and so on. Yeah.
Yeah, steps
If changes, how can you do this in the smartest way? Yeah.
Yeah. The box container network is useful for many other distribution things, so why not use
Yeah.
it for CO2? Yeah, that's fantastic. Well, that's great. Well, I guess we'll finish there, and thank you very much, Henrik. I hope you get some interesting inquiries following our
Thank you.
webinar.
Please check our homepage and please contact us directly. Yeah, thank you very much.
Pass back to Farah for the closing words. Cheers.
Yeah.
Thank you to Henrik Madsen of DecarbonICE and our audience for taking part. Contact details and a video link should be sent to you soon if you have any further questions. Do check our website to book for our next webinars and events. Goodbye.
Cheers. Bye-bye.
Bye-bye.